clap a little bit? All right. Conformity, nonconformity within the math world. Right? Where am I going to go with this? I don't know. Doing some thinking, wrote something up. So we'll start at the beginning. I just need a volunteer to do an easy project. You, good, raise your hand. Yeah, you in the plaid shirt. Hey, Dave, no, you're good.
Okay.
Count to 5 for me.
1, 2, 3, 4, 5.
That is the standard answer. Right? What was he missing? No. Back at the beginning, when people actually started counting, they counted and they started with the number 1. Right? 1, 2, 3, 4, 5. What was he missing? 0. Did not exist. Phenomenal. Well, let me get my first slide here. 0 wasn't even a concept of a number. So you're talking, your natural numbers are 1, 2, 3, 4, so on and so forth. 0 was not accepted into our numbering system until 526 AD. Does this make sense? 0 was not a number. All right? Think about the Roman numeral system. What's the symbol for 0? A little louder?
There isn't one?
There isn't one. The Romans didn't even have a 0 in their system. They started off with 1. Right. But they knew how to count. So as you're counting sheep or counting corn or whatever, right, bales of hay, they would actually leave a space between. They would write nothing there. That represented that space did not have a number because the concept of 0 was not there. Now, Babylonians. Where's Babylonia? Close. Right? Anybody know where it's at? Actually, huh? The Mag Greece, below Greece, Iraq, Iran, in that area, right? Very knowledgeable. They actually used zeros as just a placeholder. They didn't have a concept of a 0 yet. But they did use a 0 just as a placeholder. Now, the problem was, if you did not have a 0 as a placeholder, if you wrote the number 4, what is it? Is it a 40? 400, 4,000? There was nothing that they could put in there. They actually, as I was doing research, they actually put null in there. They actually wrote null, means there's nothing in this spot. Right? So my question is to you. Why was 0 so hard to comprehend? What?
Because it meant nothing, or it's a placeholder. It wouldn't really
Okay, I'll buy that. Right?
You can't really see nothing. Like if you have 1 apple, you can see it, but if you have 0 apples, you can't really see it.
You can't see 0 apples. How many apples you got? What apples? You know? How many oranges you got? Well, there's no oranges there. Yeah. Okay. The concept of 0 was not in our numbering system until 500 years after. Okay, AD. Check my notes here. Check this slide. I might want this slide. Maybe I want this slide. Nope, we don't want that slide yet. Okay. Geometry can be traced back 3,000 years BC. Algebra can be traced back to, check my notes, 1900 BC. Geometry, Egyptians, Babylonians, the Romans were using geometry without the concept of 0. Does this make sense? How can they do that? Well, they did it. Algebra, they were doing linear algebra, they were doing lines, They were doing quadratics. They were solving equations without the concept of zero. It was not conforming to their numbering system at that time. When did it start conforming? 526. We asked, the question is why? Well, they needed something. The concept was there now that, hey, guess what? Zero is actually a number. We can use it, right? After zero was invited to join the numbering system, what about negatives? Negative integers. How do you think that went over? It took them 3,000 years to get the zero in? What about the negatives? Did they conform at that time to the numbering system? No. But they were numbers. Hey, yeah, we can work. Set up a new numbering system. Those are your integers. Oh, it gets better. What about your rational numbers? 1/2, 1/3, 1/4, right? How do you think that went over? What about your irrational numbers? They did not conform to the numbering system, but they were actually numbers. So what happened? What about all your real numbers? It gets better. What about imaginary numbers? Numbers that don't even exist. How do they fit into the equation? They're all numbers. About that. So in mathematics, they come up with your sets of numbers. As the progression of numbering systems increase, all right, you start off with your natural numbers, which is your counting numbers. That's what we first started. That's been used for thousands of years. Then guess what? The zero came in. Yeah. All right. Negative integers came in. Your rationals, any number can be expressed as a fraction, came in. Real numbers. Subset of the real numbers are your irrational numbers, numbers that cannot be expressed as a fraction, but they're still numbers in mathematics terms. And last but not least, complex numbers. Mr. Dunn, what's a complex number?
Has an eye.
Has an I. It's an imaginary number. Complex numbers. Who's in Algebra 2 here? Right? You guys dealt with the complex numbers? Oh yeah, right? You can mess around with complex numbers, and guess what? You get real numbers. So complex numbers, depending on the operations, you can take a complex number, unreal number, imaginary number, do some work with it, and make them real. Questions? Awesome. All right. Okay, well, this way. All right, talk about conformity in math. Conformity in math is a must sometimes. All right? Why do we have to have conformity? Take a look at the expression on the board. 3 plus 6 times 5 plus 4 divided by 2 minus 7. And the answer is? Anybody? Without a calculator? All right. I don't know. I was working on this and I come up with a couple answers of 33.5, 28, 17.5, 37.8, 23. These are 5 of the possible answers. All right? Brad?
28.
You're saying it's 28. Okay.
Yeah, if you use
If you what?
If you use PEMDAS,
If you use PEMDAS.
just use my dear hands.
What if we didn't have it? What if we did not have our orders of operations? Right? You take a test, that's given to you. How many wrong answers are there? Dick? Whoa, the other way. If you take a test and there was no orders of operations, none, written down, how many answers are correct? Go ahead. Zero. You're saying zero. You said all of them. All your answers are correct if there were no orders of operation. Conformity within the math world. That is the problem. We ran into, we had to set the rules down. We had to set the rules down. If not, for this expression, multiple answers. Which one's correct? We have to conform sometimes. Make sense? Okay. Now, we might have some questions. You pop in anytime, chime in anytime. All right, we're not going to go there yet because I just want to see where my slide is. What was happening during this man's time? Go ahead, sir.
The scientific revolution.
Scientific revolution, the Enlightenment, right? Up to this time, what was the main mathematical processes in the world? Okay, it's not that hard, guys.
Algebra.
And
Geometry.
that's it. That's all they had was algebra and geometry, and they were very good at it. They would go to, during this time, they would go to math competitions. Yes, there were people that actually went to math competitions, and they actually earned money for these competitions. They would be given problems. These problems would be solved with just geometry and algebra. But remember, these are the smartest men in the world. Yeah, men, because I don't think women participated at this time. They would go through and sit down for days to solve a problem. They would go home, work on algebra on the free time, so when they go to these math competitions, they would win, get their name out there. And they kept those techniques to themselves. This man comes along. What is he studying? What is his main purpose? What did he like to do? Go ahead, Mr. Dunn.
Physics.
Physics. He loved physics. Newton's laws of motion. He wanted to study why things work the way they did. Up to this time, all he had in his little toolbox was geometry and algebra. And if you only have geometry and algebra, you're not going to get that far when you study physics at the advanced levels. You guys agree? If you don't, you will. All right? As you get up there. You receive credit for calculus. Okay? Even though this German by the name of Leibniz was using it 3 years before, we actually used the Newton calculus. He studied the calculus for physics. He studied it, the math, to apply the math for the physics. Question, right? As he was investigating this calculus, did he invent it? Or did he discover it? Go ahead.
I'd say discovered because the math that they're doing is just proving that those patterns or properties exist. But depending on how you look at it, they are inventing the ways of proving these things, which then be used and they're generally accepted. As if you're learning calculus, then you learn these proofs and you don't have to reprove them. But the patterns already exist because it's all just a numbers representation of things that are happening in the real world. So the stuff was happening, he just invented the numbers and the math and the different ways of working out why and how it was happening.
Yes, agree or disagree? So you're saying right now that math is discovered, not invented. Okay. Go ahead.
You could argue that it's invented because it's not something that's in the natural world. Like we have apples in the natural world, and people could discover that if you went in the forest and found an apple, but you don't just see math lying around.
Good point. So what's the correct answer, or is that? Go ahead.
Math really isn't like a physical thing. Numbers are just representing what's out there. So you can't invent, or you can invent like a way to represent something, but you can't exactly invent what you're representing.
Okay.
What did she say? Could you repeat it so others could say back there? She's using her soft voice.
Loud.
Numbers aren't a physical thing. They're just placeholders and what's representing something that exists. And you can invent a way to represent it, but you can't invent what's already existing.
Ponder that thought. All right. Age-old question right there. Check my notes. All right. You guys are too young to gamble. It's a bad thing. Don't get into it. But, check my dates here. Don't have my dates. About this time, gambling houses start to pop up, right? People go in and gamble. Well, the owner of this gambling house said, yeah, I got a problem here. I know how to run a business, but I don't know the payouts on this game. So who did he call? He actually called two mathematicians. Check the names. Pascal and Fermat. What did they do? They come in, researched all the table games, all the games, and then they set up all the odds, and they set up all the payouts. That was the beginning of probability. Why? What started the beginning of probability? Gambling. Was it invented? Discovered? No. Mathematicians are called in to help solve problems. All right. So now we got calculus going on, we got probability going on, opens up new realms. Because up to this time, what's the only two math that there were? Geometry and algebra. Now we got calculus, now we got probability. Stats comes into play. All right. We're going to test some of your beliefs in mathematics. All right. Mr. Dunn, you cannot answer these. You guys all have had Algebra 1, right? Here's the money. I got ax plus by is equal to c. If I'm not mistaken, that is an equation aligned in standard form. True or false statement? Okay, let me go back to your. Is that a true or false statement? Ax plus by is an equation of a line in standard form. Right, sir?
I would say it would be true because that's what mathematicians have decided.
Very good. Very good. Yeah, it's true. Kind of. That's actually. There you go. Sometimes. Reality is an equation of a plane. There's a line that goes through, right? Think about it logically. Got a line that comes through on the board. The z value is 0. Doesn't matter what the z value is. So this line that you thought was a line is actually the equation of a plane that comes out in 3 dimensions. So you have a belief that, hey, this is the equation of a line. But reality is, this is the equation of a plane. Got a couple examples. I'm going to test your beliefs on how they conform or not conform in this plane. this thing. Yeah, there you go. Easy money. This was an easy one. All right, you guys are mostly in geometry. Algebra 2, right? And the answer is, go ahead, sir. In the back. 90. Okay. Sum of the interior angles of a triangle is 180 degrees. True or false statement? True, right? At this point in time, it's true. Not really. What if I told you that the interior angle sums of a triangle, click, click. Here, look that one. Next.
Jeez. It's not working. Can I do that? Yes.
Yeah.
Oh, do you hold it like flat?
I don't know.
Hold on, the sensor's on the
Space
bottom.
bar?
No, the sensor's on the bottom of it, so like, you hold it like flat, like when
Sometimes. Hit the button. What if I told you interior angles of a triangle sum between 180, above 180 and beyond 360? Does this conform to your beliefs? Or does it not conform to your beliefs? You have been taught up to this time that the sum of the interior angles of a triangle is 180 degrees. But I'm telling you that's not the case. You're probably thinking, Mr. Gilmore, you got a degree in math? What are you talking about? What's the definition of a triangle, ladies and gentlemen? Three-sided polygon, right? Has three sides. That's prop, right? Take a look. Take the international date line. I'm going to drop this line from the top all the way down to the equator. Is that a straight line?
Yes.
You said no. It is. Did you say no? It is a straight line. Right? Trust me. Is that a straight line? The equator. Huh. So what's the intersection between this straight line and this straight line? 90 degrees, right? You agree? Let's drop another longitude down. Right? Longitude, let's drop it down. This longitude, is that perpendicular to the equator? What's the interior angle here? 90 degrees. Is this a straight line? That's a straight line. Is the equator a straight line? Is that a triangle? Huh. Okay. So what I'm going to do, ladies and gentlemen, is I'm going to close these up. I'm going to make the angle up here really small. 180, 180. You agree? I'm going to take this longitude and I'm going to move it all the way over here, right before it hits the great circle all the way around. So what's the angle up on top? It's 180, or a little less than 180, because if it was 180, I would not have a triangle. 90, 90, almost 180. A little less than 360. Interior angles of a triangle. They can range between 180 and 360. You agree? Does it challenge your beliefs and what you've been taught at this time? Awesome. Get you thinking a little bit. All right, got a couple of these. We're wrapping it up here. Oh yeah, this one's easy. Geometry. Parallel lines never meet, right? Right? Two parallel lines, cut by transversal, you guys know all those terms, right? Two parallel lines, do they ever intersect?
Supposedly.
No, right? Of course not. That's what we've been taught. They never meet. Well, guess what? Guess what the deal is? They actually do. challenging what you know. Do they conform? Do they not conform to what your beliefs are? Easy money, right? You guys ever sit there on the railroad tracks and look down the railroad tracks? Right? Two railroad tracks, right? They have to be spaced evenly apart, or else what would happen to the train? But as you look down, what do those tracks do out there? Do they meet? Where do they meet at? They actually meet at infinity. Parallel lines do meet. They meet at infinity. Sometimes they do. Help me out here. Right? At this point, international date line, longitude, right at that point, are these two lines parallel? At that point, are they parallel? Yeah, they actually are. They both go straight up. They're equal distance apart, right? Who do they meet? At the top. At this point, they are parallel. I'll guarantee you that. They meet on the top. Last example. This is an easy one. Everyone's going to get this one right. All right.
I learned nothing.
You learned nothing.
Evidently.
Okay. You'll like this. What's five equal?
I guess that's 10.
Huh? Come on, it's easy money. Right? You get this on a test, you're going to write 10 down, you're going to move on, right?
It's going to blow my mind.
Guess what 5 plus 5 really equals? 0, 1, 2, 3, or 4.
I told you guys.
Ladies and gentlemen. If I take 10 and I divide it by the number 5, what's my remainder? Zero. Just bear with me. Okay? If I take the number 10 and divide it by 9, what's my remainder? Divided by 8, what's my remainder? Divided by 7, what's my remainder? If I divide 10 by 6, what's my remainder? Divided by 5, what's my remainder? 0. Did I say 5? I meant divide by 5, it's 0. If I divide it by 4, what's my remainder? So if I divide it by 4, I get a remainder of 2. If I divide it by 8, guess what my remainder is? 2. Guess what that makes 4 and 8? Mr. Dunn, am I telling the truth?
He is. It's very important in computer science, actually.
Very
Something
important.
called modulo. Like, for example, you can divide 10, and if you mod 2, you can figure out if it's an even or an odd number, which is very helpful when you're designing programs.
Okay. Thank you. So you're going to get to my. All right. So from the examples, does mathematics conform or not conform? Does it conform or not conform? Just think about that for a while. I have given you so many examples, everything I tell you is true. All right, when it comes to mathematics, I do not lie. Except for the history, my numbers might be a little off on the dates, but I'm close. All right? All right. All right, a couple more concepts. When does a certain mathematical concept apply in a situation? Right? When does it apply? When you can prove it. I tell my students, do not take anything for granted. Teacher gets up in front of you, gives you an equation on the board, there's two words that should be coming out of your mouth. Prove it. If that person cannot prove it, you better prove it by the next day, because we got Google now, you can look up the proof, right? Means nothing. If you cannot prove it, it means nothing. In mathematics, once you have the proof, you're good. Then it works all the time. Right now, you guys are dealing with numbers. Math is logic. In order to use that logic, you have to show that that logic will work all the time in any situation. Mr. Dunn, do you like writing proofs?
No.
They're really rough. They're really rough. Okay, so my question is to you. What is the product of two odd integers? Is it even or odd? Who said it? You. It's odd. All right, prove it. Prove to me, beyond a shadow of a doubt, that two odd integers are odd. Anybody want to give it a shot? A little louder. Oh, what's 3 times 5? 15. Two odds. Multiply to 15. 15 is what? Odd. All right. What else we got? Go ahead.
You can never multiply even numbers to be odd, so 2 can never be an odd number if you multiply by anything.
So you're saying if I multiply an even to an odd,
It'll still be even. It's impossible for the even number to become odd.
prove it.
Multiples of 2.
Huh?
Multiples of 2.
Give me an example.
2 squared is 4.
Okay.
And a cube's 8.
Okay.
If you add 1, it'll be odd. If you add 2, which is multiplication, it'll always be.
What about 2 to the million? What about the 2 to the millionth and 1? 2 to the millionth and 2.
Let's keep going.
What about 2 to the 5 million? Just bear with me. I know what I'm doing. So how many examples do you have to go through to show me that all the evens multiplied to an odd will always be even? Will it work every single solitary time? Or you're just taking your examples that you're giving me, right, and say, well, it works, I'm going to accept that it's true. But it has to, in order for it to be true, it has to work for every single solitary example that you can give me. And how many examples are out there when you're multiplying two odd integers? It would never end. You would be multiplying, just to prove it, you would have to use infinite numbers, infinite times. So how do we get around that? Well, all right. I'm going to prove it to you, kind of. All right? First of all, we have to have a definition of an odd number. What's an odd number? Well, the man in the back was correct. It is 2k plus 1. 2 times any integer will be even. 2k, where k is an integer, is an even number. You add 1 to an even, you're going to get odd. So what we do, I don't have my pointer. All right. Multiply. Remember, this is just an integer. This is just an integer. You multiply it out. You get 4mk. mk, two integers multiplied together are what? It's still just an integer. 2 times an integer, it's still an integer. 2m plus 1, they're all integers. We factor a 2 out, leave the 1 over there. Factor a 2 out. 2mk plus k plus m. What is this? If I add, multiply these plus these, what type of number is it? It's still an integer. What's the definition of an odd number? 2 times any integer plus 1. What is this? That's an integer. This is a proof. No matter what integers that you take, right? 2 odd integers multiplied together will always be odd. We stand by these proofs in a mathematical concept. That is our truth. Right? Does it work? All right. Final note. Most mathematics is used as a tool. The branches of mathematics, the modular arithmetic, 5 plus 5 is equal to 0, 1, 2, 3, 4. That mathematics came about from the study of computers. We got a whole new branch, right? Computer science. They needed our help, mathematicians' help. Guess what? We discovered or invented, the choice is yours, a whole new branch of mathematics, modular arithmetic. Go back. Gambling. They called them mathematicians. What did they just discover? Invent. Whole new branch of mathematics called probability. Newton wanted to advance his career in physics. He couldn't get that far. What did he invent or discover? Calculus. So what is mathematics? Does it conform? Scratch that. Spherical geometry. People started studying geometry on a sphere. New branch of geometry. That's where some of the interior angles do not add up to. Parallel lines do meet. Right? Okay. There are some branches of mathematics that they study just for the math's sake. They'll invest hours and hours. Number theory is awesome. Just to play, find out what's going on. So, why are we investing so much time in these areas of pure math? That's my question to you. Why do we spend so much time studying these areas of mathematics? We don't have any application for it. Yes, Mr. Eisle.
I'm incredibly fascinated by the intersection between math and everything. And when we do in theory of knowledge, mathematics, and kids start to see it as a universal language that can be an art form, and its intersection with science is obvious, the different sciences, but you can see it in language use, you can see it just about anywhere. And I can see the idea of studying math that isn't applied being the concept of studying math that isn't applied yet.
Very good.
That philosophically, if you can imagine it, it can be invented or it probably exists. And if you can mathematically prove something, and we see it in astrophysics all the time, right? We do mathematics to prove something's there, and then later we find, oh my gosh, it is there, we proved it on paper in math class first, before we even knew that it actually existed by using our senses to prove it to a certain degree. My question for you is, because a lot of people have talked about, the lecturers have talked about anomalies and outliers as far as rules go. So science and philosophy talk about it. Can you talk briefly about it? Has there been, we'll use a cliche example, for a long time, science thought this, then something was discovered and it changed. How, the mathematical rules that you talked about earlier, like we have to have these to conform as a foundation or a basis to move forward with other maths. Has there been something within the realm of mathematics that's taken place where the rules of math have changed because, or something that was revolutionary in math, or something we believed before in math and then it was changed? I mean, does that really just fall along the lines of slow progression of some of the things that you showed examples earlier, or is there been something?
Yeah. So it's a slow progression as we get more familiar with it. The classic example is three space. For the longest time, we could only do math in three space, X, Y, and Z axis, which is the third dimension. Actually, within the mathematical world, we can prove from a physics standpoint also, because we needed to do the physics, there are 11 dimensions of space. All right. So at one time, yes, mathematically, yeah, we only worked in three dimensions, but as we progressed and moved on, the mathematics got to the point that yes, we can prove that there is actually 11 dimensions.
Which is so hard for a kid, anybody to
Oh, I can't see.
Yeah.
I can't even see 4. All right. If you close one eye, you can't even see 3. So yes, it does. As the mathematics progresses, then yeah, oh yeah. See, Einstein just blew him out of water when he started writing his papers. I mean, people read Einstein's work like it was a novel waiting for them to be published, because you're going to have leaps of knowledge, So Stephen Hawking's, okay, just classic examples of where my knowledge level in mathematics is about right here. The people that write and think on the ceiling or above, my brain is not wired the way that they are, so I just have to read what they're writing and try to understand. Any input, Mr. Dunn?
Well, give an example of Einstein. This year they found gravitational waves within the last year. It's something that he predicted over 50 years ago, and they're like, yeah, you're probably right, and they finally have been able to detect them using instruments that have now been invented with technology we have. Back then, he had no way of physically proving it. Today, we know they exist.
There is one classic. There is, you guys all know, given a right triangle, a squared plus b squared is equal to c squared. Hopefully your geometry teacher did prove that to you. That works all the time. Fermat's last theorem says, this guy who's out there, a cubed plus b cubed will never equal c cubed. And he walked around and he had a journal, right? And he goes, yeah, the proof of this is too long that I cannot write it in the margins of this notebook. Right? He left it at that. It took supercomputers to actually prove that statement true, that it will never equal, because guess what? I can make a statement, but if you cannot prove it, it means nothing. And I think, on a final note, it's a tool. Yeah, we're done. We're done.
Awesome. Usually at the end, I know there's only a couple minutes, technically we go 11:44, but usually we spend a couple minutes just asking any general questions, anything you thought of during this lecture that you would like to ask Mr. Gilmore and myself that maybe fits into your ideas for your cross curriculum?
All questions must be in writing, submitted the day before. Go
All
ahead.
right, go ahead, Kelly.
Well, it's not about the project, but it's about back to the standards.
Yeah, for sure.
Would, like, that small, like 6.5, would that be considered
That is,
like,
that is a rational number. Rational numbers are any numbers that can be expressed as a fraction. So like 0.25 is 1/4. That makes sense? So it falls in another subset of a real number.
You remember that, like complex numbers and then all the bubbles inside?
So as these numbers, my point was this, on those number sets, as these numbers did not conform, right, what did we do? We made a new number set. And that's the same concept I was trying to explain when you come up with math is an invention or discovery, right? Choice. But when math is needed, mathematicians will come in and figure it out. You know what I mean? And they will prove it. Does that make sense?
I think it's the infinity example.
Go ahead.
It's the GeoGebra, right? Infinity by itself.
When you divide out
Which part? Like the what part?
you are actually changing the equation. So let's say that you have a quadratic or a quadratic. One of the factors will actually be you're changing the equation. But when you go through and figure out the whole, you have to apply that to the equation you're starting with. For an example, you have a quadratic divided by a binomial, and the x minus 1's cancel out, what you're left with is a shift. Well, that's not the original equation. Alright? So now.
All right, guys, go to lunch unless you want to have a question for Mr. Gilmore.